I guess we can start. So my name is Christian Altenbach. I work at UCLA since 1985. I have some weird titles on top of what I'm doing. And I use LabVIEW more or less just for fun and to solve any computing problem that I run across during my research. I work in the Stein Eye Institute. And so I'm not Dmitri. Yeah, he had that slot, and we had to switch because his flight got cancelled. So maybe half of you can leave now. So the talk is about, the title is Invariant Attributes to Sets and Maps. And for those who heard Darren just now, there's a brand new first-class data type in LabVIEW. There are two different ones, set and a map data type. And we're going to talk about what they are, what is a set, what is a map, what we did before sets and maps. For example, variant attributes were sort of a clumsy way to get around it. Very high performance though. We look at what's in the new palettes, and why are maps and sets so brilliant. They're really useful for simplify a lot of programming problems. And where do they really shine? Performance, code simplicity, both. And how easy is it to adapt legacy code if you have old code based on variant attributes? How easy is it to convert to sets and maps? Very easy. And we're going to show a lot of examples. We show performance, we show code alternatives, how we take old code and rewrite it in terms of sets and maps. So there is a new item. If you open up LabVIEW 2019, there is a new item in the top level palette, and it's called collection. Nothing to do with a collection agency or anything like that, but it's right there. And there are two sub-palettes. One is for the map and one is for the set, and each one has its own function. So, sets and maps and variant attributes and all that, it's all about efficient storing information in a way that it's efficient to access that information later. For example, a phone book that's not sorted is very useless unless it only has like 5 names on a little sheet of paper. Then it's good. It doesn't need to be sorted. You can just look at all of them. But also, whenever a phone book changes, some of you young guys don't even know what a phone book is. You would need to reprint it with every data change, and that's also very expensive. So what are better ways around that? Similar, I took that a couple of weeks ago at UCLA, and it's just absolutely silly. That's the elevator panel, right? So the key and the map, it's a key. We know the floor that we know to press. For example, A, there are 3 equidistant buttons right next to A. Which one is it? Is it on the right or the left or at the bottom? So this is, I always have to do a double take, 6, then you press here, no, it's out, no, which one is it? And so it depends a lot how things are arranged for efficient access. So having information is useless unless we can find it efficiently, right? I mean, that's Google's business, right? Finding information. And sets and maps are optimized for storing information and answering simple questions about the collected data. For example, does this entry exist? A set, for sets, it's does an element exist? For maps, does a certain key exist? And then if that key exists, does it have, what is the value that's associated with it? And they're optimized for dynamic changes in their data. We can add an entry, we can remove an entry, we can replace the value if in the map, and so on for the given key. And all these things are very efficient. So let's go back. Last year, I gave a similar talk and like the last quarter of it was about variant attributes, and that's the only thing we had before sets and maps to store key value pairs. It's an attribute name and variant attribute name is the key, and the value of that variant attribute with that name is the value. And so we had, there's also waveform attributes, which are the same thing. You can actually mix and match, and all this works. You know, it doesn't care if it's not a waveform. And so they use the same underlying thing. So basically we have a variant, and it has something, has an attribute, right? The variant attribute. And in most examples, we don't even care about the variant or the waveform if you use waveform attribute. So it can be an empty variant. So why do we need that? We don't. I mean, they could have added it to a Boolean, right? The attribute of a Boolean or attribute of a numeric or of an array, but variance is sufficient. We don't even care about it most of the time. So now, as I said, a map is basically the same thing as a variant attribute collection, right? They're very similar. We have key value pairs, and the key must be unique. That's absolutely required. We have high performance lookup, insert, and delete, and we have hierarchical possibilities. The value can be a map, a set, or a variant, etc. There are also differences. They're very important. Map. For maps, the key can be of any data type. Could be a 1D, double array, can be an enum, can be whatever. Variant attributes, the key has to be a string. So we have to like typecast anything to that string in order to have a key for the required data type that we're using. Maps don't have any reserved values. Anything can be a key. Variant attributes, that's relatively dangerous. The key cannot be an empty string. You get an error if the key is an empty string because it's a sentinel value. If you get all keys internally, I think it uses like empty key and then it does something else. So all values must share the data type. Variant attributes, it's a variant. You can actually mix. Some attributes can be a double, some can be Boolean, and so on. Some can be a string. Of course, then later to unwrap it, you need to know what it was, so that makes it a little more complicated. It's probably better and cleaner if you have one data type for a given map. The data type can be anything, but for a given map has to be constant. Right. Yes.
I assume that since they all have to be the same data type, you can make that data type a variant?
Yes.
Okay, good.
Yeah, I think I mentioned that. So you actually can reproduce the old behavior by making the data type a variant. Yeah. And map is a first-class data type. Variant attributes are tacked onto often irrelevant variants, and that's sort of ugly to begin with, right, for a programming purist. So what is a set? There are three sets. So which one is actually a set? Only the one in the middle is a set in the LabVIEW definition. It's an unordered collection of elements, all sharing the same data type in which duplicate elements cannot exist. Right? Here we have 5 cups of the same style. You have all the pawns are the same. So this is not a set. Here, that's a set because all of them are different and they need to be sortable in some way. You can sort them by the RGB value of the head, right? So that's a set. This is not a set. The data type can be almost anything, and I show you how to do that. Yeah, so that seems, at first glance, it seems restrictive, but this limitation that you don't allow duplicate allows for very efficient algorithms. Now, what is a map? Right. very poorly defined. X marks the spot. Everybody uses maps to navigate. That's not what it is. A map is an unordered collection of keys sharing the same data type and in which duplicate keys can exist. That's the same as a set, right? But now each of the elements of that set has an associated value, and that value can again be of any data type. Duplicate values are allowed, and the map is basically a set where each element contains extra data. Value can be out of any data type, and you just need to know the key, and the key also can be almost any data type. It's even more complicated because a map in the community of different disciplines in science, they know it under different names too. The functionality as implemented in LabVIEW is known under many names. It's always a key-value pair. Once you know the key, you can get its value. You can add a new value by adding a new key, and so on. A map is one of the words, associative array, a symbol table, a dictionary, and in classic computer science problems, it's design data structures for efficiently do operations, like lookup, insert, delete. And it goes all the way back, and as of today, it's no longer in beta. And that's basically the map we have now. Was from 2010, so it took 9 years. But this idea is finally implemented and makes me so happy. So again, let's recap. Good arrangement of an entry, a map key or a set element. It's required to have the internal data structure. We don't need to know anything about the internal data structure, but there needs to be a way so it can be retrieved as efficiently as possible. For example, we have a set with 1024 entries, and we must prove that a certain element does not exist. If we can have no assumptions about the array of values, we need to look at every single one of them to prove that it doesn't exist. If the array is sorted, we can get away with only looking at 10 elements, because every time we look at an element, we can eliminate half of the candidates, and it really shrinks very fast. So it's a factor of 100 different, and that usually counts if it's something expensive, right? And if you have 1 million entries, then it's almost that. So the problem is, if entries are added or removed, we need to resort the internal data structures, and that's all hidden from the user. But if we don't resort, we can no longer do binary search. The solution is efficient data structure where rebalancing is cheap. We can remove an entry, add an entry, and it sort of keeps it in a way that we still can do a binary search in some way or another. So one possibility, and I'm not going to go into that much, is a balanced binary tree. Computer scientists have devised data structures that exhibit these efficient operations. There are many flavors, and research is ongoing. There's a red-black tree, I think that's what it is. There are AVL2 tree, 24234 trees, and so. And if you look at the story, for example, it took 30 years for Robert Sedgwick to make the red-black tree a little better, a little fewer lines of code, right? But there are others that say, wait, that only optimizes for code size, not for speed. So, fortunately, we can ignore all that. LabVIEW sets and maps use standard public libraries under the hood, and they're well tested and optimized, so we don't need to worry about that. So let's look on the diagram. Defining sets and maps. If you place a map or a set constant on the diagram, by default you get that. And if you have time, I can show it at the end. Maybe I shouldn't, just explain it. And in order to change the data type of the set or for the map, You simply take any structure you want, you drag it either here or here, and you define the data type of the key or the value. So you can drag this in here, it turns orange, and this here, this in here, and make a key, right? And or you can define the element of a set to be a 1D array, and go from there. So there's really, you can do anything you want, right? It doesn't have to be string, like in the old days. The default is a string, but you don't need to worry about that. And by default, they're not named. It's probably easier if we put a name on it. But you just right-click, show label, and add something. So this is just some of the palettes, right? Once we have a set, we can build sets, we can add entries, to add more than a few to make an initial map, initial set. Then you can insert into set, remove from set. You can ask if that element exists. You can ask what's the minimum maximum value. Remember, the keys need to be sortable, so there is a min and max. And the set constant is what I just showed you, where you just drop the data type that you want, or you can right-click replace with a number. It's very flexible. You can look at the size, how many elements are in there. You can ask if it's empty. This is funny. This is really good. I'll show you that later. And there's some advanced functions like union, intersection, Cartesian product. Union, right? If you have two sets, you can combine them. If they have the same data type, you get a new set that has elements from both.
So one quick question on the insert into set. If something already exists in that set, is it going to spit out an error, or it's not going to take it in?
It will tell you that it already exists.
Okay.
Yeah, there is a Boolean output.
Okay.
Yeah, but otherwise it will just go and keep it. Yeah.
Really quickly, can the key be an object in a map?
I haven't tried that. So just explore the palette. This is very quick, and we go into the details later. And so these are the advanced functions. Just look at the context help, what they do. And the code is available, you double click them, and they're all implemented as VIMs very generically. And the code is very simple for all of those. Map function similar. You have build map, insert, remove, look. And one of my favorites is the in-place map access. That's just you add something to the in-place element structure, where you then can change the value in place, or add a new entry.
Does that add to the context pop-ups when you have the place?
Yeah, you can create it there, or you can just drop this and you get both. Yeah. And the registration map, that's a sort of, it's a useful thing. You just look at the shipping examples. It's a map where the value is a set. And it's a cute little application. I'm not going to go into that because I didn't write it. Yeah. Now, how do we get the elements out, right, once we have a set? And this takes a little bit mental gymnastics, but after that say, oh wow, that's the best way. If you auto-index on a for loop, all you get are all the elements in alphabetical order or in sorted order. And if you do it on a map, you get a cluster with all key value pairs. And here you get an array of such clusters, right? Or you can process it in here or do whatever you want. And so a simple for loop lets you convert a set to a sorted array, and there's not even a primitive. It's just a structure, right? It really works well. That's the in-place element structure you just mentioned. So we have 3 different modes that you can wire here. So a map comes in, right? You can either modify entry only if found. Then it's really in place, right? Because you only change the value. but you can add and modify or delete an entry, and it doesn't need to do any copying or anything. Some are not really in place. If you add an entry or remove an entry, right, it takes up different space. And so, but the compiler, just trust it. It knows what to do. It knows what you want, what you really want. And Darren just mentioned that there is a thing called remove duplicates from array, and it's in the array palette, and that's new. And if you double click it, it just uses a set, right? And not only that, the nice thing is that the elements come out in the same order they were first encountered in the original array. Save and load, you can just dump to disk with binary read. So you write it, you reset the file position to 0, and you read it as a set, and they're equal. And if you look at it, the set, that there's no extra data structure that keeps it organized or anything. If you count it, the size is exactly 8,004 bytes. 8,000 bytes for the 1,000 doubles, and 1 for the size. 4 bytes for the size, which is a I32. So last year I presented, in terms of the variant, I presented a nice little example. I simplified it a little bit more. And that's example what it does. It generates lot of numbers. Yes.
If it's exactly the 8,004 bytes, can you just typecast it into a 1D array then?
I haven't tried that.
Okay.
Yeah. Play around. Make sure, but make sure it's right. Yeah. So, I mean, you get a particular set of Lotto numbers. Probability are very, very low. But if you generate Lotto numbers as fast as you can, and check how long it takes until you get one that you already generated a nanosecond earlier, that's actually quite probable. Interesting enough. It's similar to the probability that 2 students in a class have the birthday on the same date. So the individual probability is very low, but the more you have, the more comparisons you do, and the more chance you get that it matches. So I did 4 different implementations. Linear search. Each one I cast it to a string, add it to a string array, and then I search in that array if it already exists, and stop when it does. If it does. A binary search is much faster, but we have to keep the array sorted, so we have to do a smart insert to keep it sorted, which requires quite a bit of code and debugging. We can use variant attributes, where we flatten the Lotto number array into a string and add it as a name, and we don't even care about the value. It's just the variant name is sufficient, and wait until we get something that we already have. And of course the set. And these are the 4 code variations. I said, when each new entry, this generates n Lotto numbers. It flattens it to a string, adds it to an array, and if the entry already exists in the array, it stops the loop, tells you how many iterations it took. This is the fancy one, and all the secret is in that little sub-VI here, and we're going to go into that. With variants, again, we can't use the array of Lotto numbers. We have to flatten it to a string, and we have to wire a value even if we never care about it. In the set, of course, there is no value. It's just a collection of items. We just add it to a initially empty set, and once it already exists, we stop and get the same output. A close look at the second version, we do a binary search on the string, so we have to make sure, have to prove it's sorted. the nice thing is once you do a binary search and you know and you prove that it's not there, you also have the position where to insert that. Of course, once the array gets really big, that's expensive. If you insert at the very beginning, arrays need to be contiguous in memory. You have to move all the higher elements one up in memory, right? So you have to rattle through the entire thing. But the compiler is really good. You can do that unless it gets really big. So quickly do an example here. Let me sit down. Okay. Lottery numbers benchmark. And the problem is the outcome of every generation is random, right? Sometimes it takes longer, sometimes it's shorter. So what we do is we do it repeated many times for the algorithms and see how it scales with the number of tries needed. And we start with 5 lottery numbers between 1 and 69, I think. So if I now start running that, then we see that all that the insert, the smart insert, the variant, and set are really neck to neck, right there in the middle. Whereas the append, since we have to search through a longer and longer array, it gets really dragged down. And you see it here. This is a linear scale. This is a log-log scale. So these are really large orders of magnitude. If you go to really small sizes, here you can set the size to less. Then you see it fills down here. Down here, it doesn't really matter what you're using, right? They're all super fast. But if you then go to like to really large, I mean 9 lottery numbers, right? It should take, it takes 1 million times on the average, 100,000 to 1 million to get it. And now if you look at that, what the VI actually, with every new data entry, what the VI does, it does on the log plot, it does a second order polynomial fit. And if you move that thing around, you can see that at 1K size, the time is 70 milliseconds, 444. So the set is fastest. Variant is not as close behind. This is really fast too. Oh, it's even faster, right, with the smart insert. But they're within 10%, and the search is already 4 times slower. But if you go now here, let's say here, you see there's a set and variant are within 10%, but now the other one is already, this is not right, that number is not right. Oh no, here, the orange is 1,000 times, 780 times slower if you do this search. So it really gets really expensive, and if you go here, you probably get a mega year or something. Yeah, it's 33,000 times slower. But if you can, here down in the linear, you see that they're really neck and neck, the set and map. And it's I probably can adjust the code a little bit. Sometimes map is a little faster, sometimes variant attributes. They're really the same. So fill in some more points here. Let's see, 7. Yeah, you see how the red now starts getting expensive. And so let me stop that and continue with the slides. There's an F key right for that. Oh well. Okay. So just in summary, you see that even the best binary search and smart insert runs into problems once you go too very big, and that's because arrays need to be contiguous in memory, whereas sets and maps don't need to be, so it's cheaper. And if you only have about 10, 100 elements, it doesn't really matter what you do, right? So let's look at the code, right? The brainless append implementation is slow and scales very steeply with the number of tries. gets impossible for large N. A simple homemade insert implementation use binary search, use smart insert is competitive, it's nonlinear, and gets expensive at large sizes. Variant attributes and sets scale well and it's quite similar. Maps is slightly better below 10K, Venture maybe slightly better above 10K, but this is I only tested on this laptop, and this is pretty old process, so this might change. So set implementation clearly has the cleanest code, so the winner is definitely the set. So some of that's how much time do I have? Another 20 minutes, I guess. Yeah. Okay, let's revisit the examples that I presented, where I demonstrated how nice variant attributes are, and now we can see how much nicer maps are, right? And side by side. So map examples. We had a little database of key value pairs, and we put those in a variant as name, and then we can just look it up, and if it can't find it, it responds with the default value, which is the not found, right? And as soon as you type a new letter, it asks if it's found or not, it tells you if it's found or not, and it found what it is. Very simple code, right? I mean, I'm not going to show any complicated code in the talk, because nobody's going to remember it. So how do we convert that to map, right? The thing we need to do is change the variant into a map constant, and by default it comes as string and I32, I think. So we just right click and replace with string in here, right? And the same code is basically the same code. We just replace set variant attribute with insert into map, and to get it out, we read from map. We have a default value, not full, not found, fruit name, and we type a letter. And the function is exactly the same, except now we don't need to know anything about variants, right? This is really confusing to some. I mean, now it's a map, right? And we look up in the map. And as you can see, the connectors between the two are really pin compatible, right? You just pop that out. You can right-click replace with the map equivalent, and it does it. You don't even need to rewire it. It took me like a minute to convert that. So I guess it's clear to see. I have a little thing where I can do it online. Let's not do it. So, and if the data is really static, you can even do the set directly, so you don't even need to insert it. The thing is, you cannot edit the set constant, but you can right-click, create an indicator when you create the first set, and then run it once, and then change that to a constant and tap it into the diagram. This is another one. You can take a long string, like Shakespeare, Hamlet, or whatever, and do it, read it as a space delimited string, turn it into array elements, and then whenever there is a new word, increment the number. By default it's 0. Whenever we found the word, we increment it by 1, and after a while, at the end, we have the words as attribute names, and the value is how many times that word occurred. Then you need a lot of gears to get it out of the variant. We have to tell it what it is, and so on. And then we want to sort it by unique words, and so on. So we have to bundle it back and sort it, reverse it, so the highest frequency words are on top of the list here. So this is confusing some, right? Anything that has a gear on it is very mechanical. Let's see how it looks with maps. And now we use the in-place structure. We say the default is 0. And as soon as we find an entry in the words, we add and modify, right? So if it's not there, we add it. Otherwise, we increment it by 1. We take the old value and increment by 1 to keep the number of words for any given word. And then again, we auto-index on that map. At the end, get the 2 out. Here we reverse the order. There's sort of a trick, so it now sorts by the number here and show the statistics. Everything else is the same. It's just this is much easier to understand code.
Aren't they already sorted coming out of there? Do you need to do the resort?
No, I want to sort them by number of occurrence.
Oh, number.
They're sorted by key. Yeah. You can stack things, and that's an old forum example. You can click on the link in the presentation and you download it. And it's a weird question. I don't get it why we need that, but I implemented it. Basically, it has all that huge array with arrays inside arrays and then clusters. And for each unique element in the first column, we need to find all unique elements in the second column. Right? So again, we iterate over that. We add all the keys, and this inner one, we don't care about the value. We just want to find the unique elements. So again, it's a waste for the variant attributes to even have a value. At the end, we need to sort of crank it out and auto-index and get that kind of value out. If you do a map where the value is a set, right? The internal value is a set. We do the same thing. We do the in-place map, replace, and we have an empty set at the beginning. And every time we get a new entry for a given value, for a given key in the map, we add a new value to the set, so that grows. And at the end, I said you just auto-index map to array and append it here, and we get the desired output that we have up here. So arguably, again, this is much simpler. One thing you have to be careful of, add or modify is not the default. So you have to make sure you wire that. Otherwise, you only get already existing entries. And since we start with an empty map, we won't get anything interesting at the end. At NIWeek 2012, I demonstrated something that I need in my research, which is a caching application. I have a very complicated function that has many parameters as input, and often some of those are the same, and I don't need to recalculate the function because recalculating the function is very expensive. So, and especially if you do like fitting, the partial derivatives, oftentimes certain parts are constant between iterations, but I also allow every parameter to be the fixed or fittable. It would be impossible to implement all that logically. So I do it in a map, basically, where the map is the set of all parameters. The key is the set of all parameters, and the value is the spectrum that comes out. The other problem is that it's very unlikely that I need a map entry that's from last year. Usually, it's only important to have the map entries for the last 5 minutes, maybe. So, if I would grow the map forever, add every new entry, we have a lot of garbage that we never need to look up, and it's going to be really slow. It's getting really slow. So what we do is we check, and I keep extra information about the age. Whenever something comes in and the cache is full, I find which one is the oldest, throw that out, and add a new one in, and then reassemble the spectrum. I'm not going to go into that, but it really, except that to say that it really improves the way if you have a lot of cores. This one has 32 cores. It really, once you allow parallel execution, it can calculate all the spectra required in parallel, and the cache sort of acts as an arbiter, as a critical section to decide if something needs to be calculated or not. Yeah. So, and this is a very preliminary benchmark. It took me literally maybe 10 minutes to take that entire BI and just replace it out, the variant stuff, and replace it out with sets, with a map, with the map-based thing. And if you look at it, if you do search instead of a map or set, you see that there a lot of them are really slow. That's a histogram of all possible and logarithmic sequence. So it's like, yeah, 100 microseconds, 10 microseconds, and so on. If you do variant, it's very tight. It's always fast. If you do map, it's also very fast, and they're very comparable. And so far, I found that for if the cache is really large, the variant wins slightly. If it's slower, then the map wins. But I'm sure that this can be improved under the hood. And I only had that release version of LabVIEW 2019 on this lowly laptop, and it will probably be much better on a faster computer. So I will redo these benchmarks once I can install the real VI. So, should we upgrade? If you have I don't know how many of you used variant attribute lookups, maybe nobody, yeah. So the question is, should we upgrade or not? Should we change to maps? And if it's working well, there's no real need to upgrade. If the old code is clumsy with complicated data types flattened to strings as keys, right? And you have to deal with possible empty strings as key, where you need to do exception handling, it might be worth it. So upgrading is typically very quick and inexpensive, not a huge barrier. You just drop that. Of course, any good programmer knows all modified code needs to be tested and verified. So this is probably the time-limiting step. You have to make sure that it really works under all conditions, as before. And maybe benchmark it, see what the speed is. For all new code, I would highly recommend using maps instead. It's so much more intuitive. And they're right there in the palettes, and they're very clear. The implementation that NI did is really nice. I mean, it's all the functionality we need, and it's very functional. All the tools are right. They're pin compatible with the old variant stuff. And the auto-indexing is a great idea to get the elements out. Don't upgrade if you potentially need to convert down to 2018 or lower, because maps and sets don't exist in these versions, right? So, I mean, you're stuck in 2019 and newer once you use maps and sets. If not all variant attributes have the same data type, make the map value a variant. That's what Chris said. So you can do that. But now we have two. We only had variant attributes, but now we have sets or maps. You have to make a decision, right? Use variant attributes where we don't care about the value. If we have variant attributes where you don't care about the value, and I showed already some examples, replace with a set. If we care about the value, we replace with map. If the key, that means the attribute name, is cast to a string, consider using the primary data type of the key directly, and we can now use anything we want. Replace all the functions with equivalents, nearly pin compatible, as I showed. Don't forget to invert the Boolean output. There's one change, and that's very important to know. If you just blindly replace these two functions, look in map versus get variant attribute, is there's a Boolean output which is in the variant, in the map, it's key not found. It's true if the key is not found. If you get the variant attribute, it's if the key is found is true. And the map is much more consistent with all error handlers. Usually if the Boolean is true, then we have something that we don't want. And so just insert a not in there, or change the stop condition of the loop, or whatever hangs off that Boolean. But that's really the only thing where you need to switch something. So guidelines. In order to find a certain entry, the keys need to be binary identical, with one exception. We don't get any closest match, we don't get any interpolation, or any of that, right? We can't say which entry is most similar to what I put in here if it's not found. So you have to be really careful with floating point data type keys, right? If it's single, double, complex, sometimes they look exactly numerically identical, but there is a wiggle in the last bit, and you will never notice, but it will not find it in the map again, right? Of course, you can somehow work around that by masking up certain bits, but it's a lot of work. It's just important to be aware of it. So NAN is allowed and is used normalized and equal to itself. Typically, NAN is never equal NAN. But here, if there's an NAN and you search for NAN, it will find that entry, even if the binary are not the same. Yeah, there is an almost infinite number of NANs. If you look at the bit pattern, only certain things need to match to be NAN. And so even if the bits are different, it will say, oh, it is. There are no built-in limits in hierarchical structures, but our brain has such limits, so keep it simple. Don't do a map in a map of a set or something like that. It doesn't make sense, right? And you run out of memory. And keep the data typically on the diagram. So don't use controls and indicators for maps and sets. They're useless, except for connectors for sub-VIs. And I would recommend to encapsulate the set of map in a single sub-VI and just access that to look it up. Don't carry it around, across sub-VI binaries up and down through the entire project. You can keep it in a DBR, and apparently there are opinions about that. And of course, we don't have any reverse lookup because values don't need to be unique, right? But of course, if you need that, you could implement it as two maps. And whenever you add an entry, you can make sure that there are no duplicates both ways and add it to both and wrap that into your own tool. I'm not sure how useful that would be, but it could be done. And so sets and maps, in summary, are highly welcome addition to LabVIEW. Really great. They help solve many common programming tasks with simpler code, easier to understand code, and faster code. And I only touched the surface. Very, very simple, easy to understand diagrams. You can make your own big thing out of it. But it's really, I encourage anyone to dive in and upgrade to 2019 and start using this because it really solves a lot of problems. And sets and maps alone make upgrading really worthwhile. I love them. They're really great. So feel free to ask questions. If we have time, I can show some examples, but maybe we just stop here. Yes?
I asked Darren if it can be an object, and he said yes.
Okay. Yeah, I would think so. I mean, it's very complete. I dropped almost anything in there, and it never gave me an error. Yeah.
We do technically have 15 more minutes if you do want to show.
Okay. Yeah. Okay. Yeah. Let's get rid of the questions first. Yeah.
And how does the lookup time scale with the size of the data type? For example, if the data type is a large waveform, that type of thing.
I haven't done extensive testing, but it always scales with log 2n, right? So it's just, it doesn't tell you anything how expensive a single comparison is. So it scales with the complexity of the comparison. You have to be able to tell which one's bigger whenever you have an entry, right, with whatever's in the map. And so that comparison, of course, gets more complicated the more points are in there. I don't know how well they are. I mean, if they're really different, it needs to only look at the first element and say, hey, it's different, right? But to prove they're identical, it probably needs to look at all of them, and then you also run into problems with double, right? So it's probably not such a good idea to use a waveform as a key, but I mean, you can try it.
I wasn't going to, but.
Yeah, okay. Yeah.
Interesting question.
Yeah, it boils down to the comparison operation. Okay. Yes.
How did, you mentioned that it's the lookup, or when you look up the values and then it sorts them.
No, I just say that if you know it's sorted, then you can search very fast. The problem is with once if you keep it as an array, and that array is really large, you run into memory problems because it has to be contiguous in memory, right? Sets and maps don't need to be contiguous in memory. And the way the data structure in binary trees is different. So, I mean, I don't know exactly what's under the hood, but that's what I heard is that it's easier on the handle. It's an example that if it's arranged right, for example, sorted right, you can search faster than if it's equally. But they use an even higher data structure than just a sorted array. Even though if you extract it out at the end, you get the sorted keys.
Oh yeah, that was kind of my question. The sorted keys, are those sorted concurrently, or is
when you try to get them out, they always come out sorted. Yes.
Oh, and how
yes.
does that sorting work? Is it like, for example, if the keys are something different?
So at the beginning I said the key all have to be on the same data type and has to be sortable in some way, right? We don't care how it's sorted, but for strings it's easy. It's just alphabetical. For numbers, for integers, it's numerical. But for other things it might be a little harder. It's just you need a unique way. If you have two different keys, you have to uniquely tell which one comes first, right? And it's sorted in that way. And I don't know in particular if it's reverse alphabetical or whatever, but it comes out sorted. Probably the same if you had an array of that and you put it through sort array, it's probably the same as you get there. Yeah. Okay, so here is a quick thing. It's a little small, huh?
Hey, Chris,
Yeah.
if I may. So one of the benefits, if you've ever had to concatenate pieces of a string in order to uniquify the keys of an attribute in a variant. So let's say that you wanted to have a name and a version, and you said name : version as a way of uniquifying your strings, your keys. One of the biggest benefits you get from a map, from what I've played with, is the ability to submit a cluster as your key, where now you could have individual values, no need for concatenation or resplitting them later. So one of the things that we did at one point was a dependency inspection, where you wanted a source and a target, where we found a unifier and we concatenated the string to make it a unique ID. Well, now you would just pass it a cluster of two strings, and as soon as it matches, it gives you your pairing, which was really fast and really easy to do with a cluster of a key, which you couldn't do previously easily in an attribute.
Yeah. No, it really works well, and there are really many applications. Okay, so here's a quick example. So typically what I do, so you just drop it in there, right? And now you have a set. So there's a double scalar. The element, or you can do a 1D array, and that's similar to what I used for the lottery example, right? And as you can see, it even takes the label and puts it in there. The label it had outside the map. And that's useful later if you index it out. You can unbundle it by name, and you get exactly what you have. So it's always good to put all the names on the elements. Like if you have a cluster, then it's easier. It's easy to index it out. And the same here, yeah, you can do a string array as value, and a complex 2D array as key. Mix and match, really anything you want. And it's as easy as dropping something in, or you can choose to replace. If you know you want a number, replace. Yeah, Darren will like thank me for that. I'm going to replace. Where is it? This one. Replace with a number, and we have a new type. And
Can you test an object?
I didn't, but he just said that works, yeah. And so we have that code I showed, right? So all we need is drop a set constant. No, a map constant, sorry.
Question when you're going through this, is there a way to load a set from a file easily?
Yes.
Okay.
Yeah, I showed, yeah, you just load it, yeah. And
But a human
even
readable
if it's
file.
not sorted, it will rebalance it.
Is there a way to read it from a CSV file or something like that? Because it was a binary format, so you wouldn't be able to go in and edit that.
Yeah,
let's
no,
say.
but so what you do is you take it and then you go into a loop where you iterate, insert into set. Yeah. You just insert all the values from that. So I create a map here, and we know replace. We know this needs to be a string. I can drop something or just say it's a string and wire that here. And now here is a replace with insert into map, thing, and here is a read from map, replace. Yeah, I don't have a mouse here. This is a little hard.
I can see this being a handy BI script here.
Yeah. And look in map, right? And tank is already converted. It's really, really pin compatible, very easy to adapt, and now looking at it, it's understandable. Like you don't need to know what variant attributes are and all that. So go out and start using it. Yeah, post in the forum if something doesn't work. Try to figure it out. Okay, thank you very much.